Hi everyone. So far on our discussions on comparators, we spoke about some basics of comparator circuits and also we looked at some commercial comparator ICs. I thought it's the right point to talk about some very interesting aspect of comparator, which is the output stage of a comparator. If you look at the data sheet of any commercially available comparators, you will see terms like open collector or open drain output comparator or push pull output comparator, or you'll also see terms like LVDS output. What do these terms mean? And what importance or significance these terms have for circuit designers who are going to use these comparator ICs? So when should you choose the comparator output type, the right comparator output type for what applications? So that's what we'll try to answer this at a very brief level. I mean, we won't go very deep into understanding these circuits. Very briefly, I'll talk about these three different output stages. So first, shown here is the schematic of a comparator, a commercially available comparator. And we have already discussed this schematic once. I've already shown the different amplification stages. We already said that a comparator is a voltage amplifier with a very high gain, right? It's like an op-amp. It doesn't have any compensation capacitor because it's always going to operate in open loop. Therefore, it doesn't need any, we don't have to worry about stability. Okay, so that's why it doesn't have any compensation capacitor. And in its construction, it's very simple. You just keep cascading as many gain stages as possible to get as high a gain as possible. Okay, so that's what a comparator is fundamentally. So if you guys recognize this, this is a bipolar junction transistor based comparator. The first stage is a differential to single-ended output comparator, amplifier, followed by two common emitter amplifiers. Okay, the first stage is a PNP common emitter differential to single-ended amplifier. The second two stages are common emitter amplifiers with current source loads, right? So if you guys see, these are all current mirrors with some bias voltage, and so these guys will act like current source loads. So they'll give you the highest gain possible in each stage. Okay, the gain of each stage will be close to intrinsic gain of this technology. If you look at the final output stage, the output of this final common emitter amplifier is floating. It's open. So such an amplifier, when if you look at the circuit schematic, then you will see the final stage will be open. So that's called open collector output comparator. So when you see the term open collector output in the data sheet, in your mind you should picturize that the last stage, the collector terminal is floating. So if this comparator was realized using MOSFETs, the last stage would be built using, the last stage will be a common source amplifier with an open drain output. So to very briefly understand this, I'm going to draw a simple mathematical model. I mean, this mathematical model will be useful at a later stage as well when I'm analyzing a very interesting property of this open collector or open drain outputs. Okay, so the mathematical model, what am I going to do? I'm going to represent this, all the amplifier stages till the last stage, till the last stages as a single differential to single-ended amplifier with a huge gain. Okay, and then I'm going to put a minus sign here. That is just to denote, the polarity. I have to just capture the polarity because if you see, a common emitter amplifier already adds a negative sign. Okay, it's a 180-degree phase shift. It provides a 180-degree phase shift. So this entire thing, including this common emitter amplifier and the common emitter amplifier with an open collector output, I want to just mathematically represent it as a differential to single-ended output comparator, which is nothing but a very high gain amplifier. And if I have to show a common emitter amplifier here, I have to show a negative gain here so that I get this relationship V0 equals A times VD. It's just mathematical. I'm just maintaining the mathematical consistency for the analysis of the circuit. So you don't have to worry about that. It's very simple. Just think about it. Why did I add -1? I'm just, for those of you who understood why, it makes sense. It's just to capture that this stage will act like a high gain amplifier with no phase inversion. Okay, that's it. There's nothing else. So now, what happens for a comparator if you apply a voltage VD less than 0? So for a comparator, if you apply a voltage VD less than 0, the output should go to logic 0, right? So if VD is less than 0, the voltage at this node will be A times VD, which will be a huge negative value. Multiplied with -1, this node voltage will be a huge positive value. So that will quickly turn on this transistor, and the transistor will discharge this capacitor. So this capacitor, assume that the initially capacitor voltage was equal to VCC. Okay, this assuming it's bipolar I'm assuming the supply voltage equals VCC. It was initially charged to VCC. It will get fully discharged to 0 volts. Now what happens when your VD, the differential input voltage, is greater than 0? If your differential input is greater than 0, then the voltage at this node will be a huge positive voltage, which means the voltage at the base of this transistor will be a huge negative voltage, which means this transistor will be cut off and the capacitor voltage will not change. There is no path to either charge the capacitor or even discharge it, because this transistor is cut off. The capacitor at this, the output is at this node is just floating. So that's the problem with open collector outputs. You cannot directly use these comparators. Okay, you have to connect create a charging path for them. So the simplest way to create a charging path is just add a resistor. So here I am showing a open drain output based comparator. You'll have to connect a resistor, and the other end of the resistor will be connected to the supply voltage. Okay, so now you must understand, I'm just going back to this -1 sign. I hope you understood that. See, I want to maintain this. If VD is less than 0, output should go to logic 0, right? So that is maintained. If VD is less than 0, this node voltage will be A times VD, which will be a huge negative value. So this will be a positive value, and that will this transistor will then discharge this node. I want this to happen, right? That's why I've added this -1 sign. So, okay, so I'll come back to this. So if you look at open collector or open drain output comparator, you can immediately see that this comparator output will be connected to a resistor to the supply voltage. So this is how it will look like. So if you use a commercially available open collector or open drain output comparator, if you are going to use it in a schematic, in a circuit, then you have to connect an external resistor through the supply, because this resistor is what that creates the charging path for this comparator's output. Okay, so that's the thing about open collector or open drain output. So even if I don't tell you the comparator type, output type, by looking at the schematic, and if you know that this circuit is a comparator with an output resistor connected at the output, then you can quickly realize that it is an open collector or open drain output based comparator. Okay, so now we'll look at the final state. See, whenever we are talking about open collector or open drain output, the last stage is of significance to us. Okay, the last stage is when what charges or discharges the output node. And one more thing, here I've assumed the load to be a capacitor. So you guys might wonder, why am I assuming the load to be capacitor? Why not a resistor? So remember this, a comparator is a mixed signal circuit. The input to the comparator is an analog voltage. It's a voltage comparator. Input is analog voltage, but the output is a digital voltage, right? It can only have 2 voltage levels. So generally it's very common for comparators to drive digital logic gates, and these digital logic gates offer capacitive loads, right? This may be driving some NAND gates or some combinational or some sequential circuits, and those circuits will all be built using MOSFETs. Mostly assume they are built using CMOS gates, CMOS logic circuits. Then this node will be driving the gates of those logic gates. Okay, gate meaning, when I'm saying gate, I'm talking about the gate terminal of the MOSFETs. So there, when you look into the gate, you will see capacitive load. So that's why I've modeled it as a capacitive load. Okay, so now if you look at this charging and discharging paths, the discharging path happens through a transistor, and the charging path happens through a resistor. When the output node is getting charged, so what is the condition for output node to charge? Your VD, the differential input voltage, should be greater than 0. If VD is greater than 0, the output will be charged to VDD. If VD is less than 0, then the these two, the final output stage transistors will be turned on and they will discharge it. So you can naturally see that open collector or open drain output stages will have an asymmetry in charging and discharging. Discharging happens through a transistor and charging happens through a resistor. And if you see the charging, since it happens through a resistor, it will be like this transistor is anyways cut off, so I can ignore the transistor altogether. And since it happens through resistor, it's a first order RC charging. So assuming the capacitor is starting to charge from 0 volts, it will roughly take 5 time constants to reach VDD. Okay, so asymptotically the output will reach VDD, but within 5 time constants we can, for all practical purposes, assume that it has reached a voltage close to VDD volts. So one more thing to keep in mind is if you look at the final stage in an open collector or open drain output based comparator, this final stage will resemble a TTL logic. Okay, it's just a common emitter amplifier with a resistive load. That's it. And for such circuits, for the charging path, this transistor is cut off, so there is no problem. The output node will be charged to VDD volts. But when it comes to discharging this gap, the transistor will try to discharge this gap. But anytime this node voltage goes lower than VDD, a current will be set up in the resistor, and the resistor will try to charge the output node. So there are two kinds of charging and discharging that happens at the output. Okay, so the resistor is trying to charge the cap and the transistor is trying to discharge the capacitor. So initially assume that the voltage across the capacitor is equal to VDD. So the base emitter voltage of this transistor will be fixed, right? So that is dependent upon VD times the gain of this amplifier, the gain of the previous amplification stages. That will appear like a huge base emitter voltage at this point, and then it will try to discharge this output node capacitance. The transistor will try to discharge it. Initially, when it is discharging it, the output node voltage will be equal to VDD. I'm assuming this node voltage is VDD, so let's not confuse between VDD and VCC. It's just a supply voltage, so I'm just calling it VDD here. So as this node, your transistor will carry a huge current because it will be in active region. Active region is like saturation region for BJTs, and then it will carry a highest current for a given VB, for a given base emitter voltage. This is the current versus VCE, output characteristics of a bipolar junction transistor. Okay, and if you see, for a given VB, the transistor carries the maximum current when its VCE is highest, and as the capacitor is getting discharged, the VCE is decreasing and the current in the transistor starts decreasing. So initially the resistor is trying to charge it, but the transistor is trying to discharge it. The discharging current is much higher compared to the current flowing through the resistor. Okay, therefore the transistor will dominate and will start discharging the cap. But as the node voltage starts decreasing, at some point this bipolar junction transistor will enter ohmic region. So ohmic region is, like in bipolar literature, it's called the saturation region. So let's not get confused with the term. This is a region where the current in the transistor starts decreasing with decreasing VCE. Okay, once it reaches this region, your current will start decreasing, and at some point the current in the resistor will become equal to the current in the transistor. At that point, no current will flow through the capacitor, and the capacitor will reach a steady state value. Okay, so if you see, the capacitor voltage does not go to 0. That's what I'm trying to drive here. So your capacitor starts off at VDD, it reaches a lower value, and at some point, assume this is the capacitor voltage. Okay, and so it's initially at some VDD volts, and then it starts decreasing. It reaches a lower value, and at that point the current in the resistor becomes equal to the current in the transistor. At that point the transistor enters the ohmic region. I can model it as an incremental resistor between the collector and emitter terminals. So that's what I've shown here. And the voltage at the output node, the low voltage level, is given by VDD times R on by R on plus R. So in an open collector or open drain output based comparators, the logic low level will not be equal to 0 volts. Okay, or it will not be equal to the lowest supply voltage. It will be slightly higher than that. Your logic high level will be equal to VDD. Okay, so if I want to increase or improve the because see, the discharging happens through a transistor, it can be very fast. Transistor can provide a huge current, so it can be really fast. And the charging happens through a resistor, and that happens like a first order charging. So discharging is non-linear process because it happens through a transistor. The charging happens through a resistor, and it follows a first order charging path, first order charging profile. If I want to improve its time constant or decrease its time for charging, what should I do? I will decrease the resistor value. That's one way of doing it. But if you decrease the resistor value, you should understand that this term will start increasing, which means your logic low level will start increasing. Okay, that's one way of doing, but it will increase the logic low level. And also another thing to keep in mind is that if you guys find the incremental gain of this comparator circuit, the final stage gain is given by, it's a common emitter amplifier, it will be GM times R. Okay, so if I decrease my resistance value, I will be decreasing my gain as well. The incremental gain of this circuit will also go down. So one other way to improve your time constant, to decrease your time for charging, and you might find such circuits if you go through any data sheets for comparators, is instead of changing the resistance value, I will now use two different supply voltages. I'll use one supply voltage for my comparator to bias all my transistors in the comparator, and I'll use a higher supply voltage which I'll call it VDD2, and that connect your resistor to the output through that supply voltage. Okay, so this VDD2 is a higher supply voltage, and the resistor's output, the other terminal of the resistor is connected to VDD2. So now if you see, remember for a comparator, for a discharge path, the transistor here will be cut off. If you guys can remember the first slide, the first point that we discussed in the mathematical model of a comparator for a common for an open collector output based comparator, we said that for a charging path, this guy will be cut off, right? There is no discharging path active. So this, if you connect this node to VDD, ideally this node voltage will just blow up to VDD itself. This node voltage will just charge to VDD2. Now if I charge this to VDD2, generally the comparator outputs will be driving some digital logic gates, and these digital logic gates will be operating normally at the same supply as this comparator VDD. Let's assume they are operating at VDD volts. When you do this, this can lead, because the output node voltage is now at VDD2, it can lead to breakdown of the transistors in these logic gates. So you have to always operate the circuits in safe voltage levels. So to ensure that the output node voltage does not go higher than VDD, one thing we do is that we just add a diode here between this output node and the supply voltage VDD. So what happens, anytime the moment this node voltage is charged to VDD volts, the diode will turn on, and it will not let this node voltage go any voltage higher than VDD. Okay, so this is a circuit that you will see. How does it do? We'll just do a quick mathematical analysis to understand. See, here the problem arises only during the charging process, right? That's when this node voltage can go higher than VDD. So what I'll do is I'll take this part of the circuit and show you guys how the charging process happens. Okay, so I have drawn this part of the circuit here, VDD2 to the output node through a resistor to an output node. So this is the output node V0, and I've connected a diode from the output node to the supply voltage VDD. So since we are focusing on the charging path, let's, for the sake of simplicity, we'll assume the voltage across the capacitor to be 0 volts. Initially the capacitor is discharged to logic 0. Here it's logic 0 is not exactly equal to 0 volts, but I'll assume it's close to 0 volts. If I assume this node voltage is at 0, and I'm assuming for charging there is no transistors are not active, so the circuit is just this much during the charging process. So initially this node will be at 0 volts, this node is at VDD volts, so therefore this diode is cut off. So this diode is cut off, so I am left with a circuit which is a simple first order RC circuit with a DC voltage source of VDD 2 volts. Now this circuit is very simple. We know how to find the voltage across the capacitor. It will be what? Assuming initial voltage is 0, it will be VDD 2 times 1 minus e power minus t upon tau, where tau is equal to RC. So this is how the graph is going to look like. The yellow line here represents the voltage VDD2. The green curve is the first order charging, is ideally the voltage across the capacitor, which follows a first order charging with a steady state value equal to VDD2. Now this node voltage starts increasing. The moment this node, the voltage across the capacitor, which is the output node, reaches VDD, this diode will turn on. Assume that this diode is ideal for the time being. If you assume this diode is ideal, this node voltage will be exactly at VDD volts. The moment this node voltage reaches VDD, the output will be now shorted to the supply voltage VDD. From then onwards, the voltage across the capacitor will remain the same, it will remain constant, and it will be equal to VDD volts. Now if you see, the resistor is carrying a finite current, and the value of the current is VDD2 minus VDD upon R. That current will flow through the voltage source VDD, right? It's a voltage source, it can sink and source currents. So that current will flow through the voltage source VDD. So whatever current is flowing through the resistor, it will flow into the voltage source. None of the current will flow through the capacitor, therefore the cap voltage will remain constant. So that's what I've shown here in the orange color. So the voltage will initially start from here, it will reach VDD, and once it reaches VDD, at this point the diode turns on and the voltage will remain constant. Okay, so shown in yellow here. What does yellow here represent? This represents the conventional first order charging, the normal first order charging using a simple RC circuit with a supply voltage of VDD. It would have taken much longer time to reach VDD volts. Okay, it would have taken 5 time constants. See, it reaches the final voltage of VDD only at t equal to infinity. It tries to reach it asymptotically. But here if you see, right, because VDD2 is greater than VDD, at some time when this node voltage when this capacitor starts to VDD volts, it will be charged exactly equal to VDD volts. The voltage will remain constant. Okay, and that time, the time at which it reaches a value exactly equal to VDD is finite. And how do you find that voltage? How do you find that time? You just take this green curve, which is VDD2 times 1 minus e power t upon tau, and equate it to VDD and find the time at which it happens, and you get a relationship that looks like this, which is RC times ln of VDD2 upon VDD2 minus VDD. See, this is something I always tell my students. Whenever you see results like this, how do you know if this result is correct? I mean, I just quickly derived it, but a quick sanity check. How do you do that? Always remember this result. For any first order circuit, let Vf be the final voltage, assuming that the initial voltage is 0. The time it takes to reach Vf by 2 volts, that is half the final voltage, final value, is tau ln 2. Okay, so remember, ln 2 is a number that is less than 1. Right, ln is log to base e, and e is some 2.8 or 2.78 or something. It's close to that, right? Close to 3. So therefore, ln of 2 will be a number that's less than, I think it's 0.7, 0.69 something. Okay, so which means it will take less than 1 time constant to reach half its final value. Okay, this is some useful result to keep in mind. So the time it takes to reach half its final value, assuming you start from 0 volts, okay, assuming the initial condition is 0, is tau ln 2. So look at this result. For the sake of convenience, I'll assume that VDD2 equals 2 times VDD. So the time it takes to reach VDD is nothing but the time it takes to reach its half value. So substitute VDD as 2 VDD, you will quickly see this result reduces to RC ln 2. So this result makes sense. Okay, that's just a quick sanity check. There's nothing too deep about this. It's a useful result, remember, the time it takes to reach 50% of its final value is tau ln 2. And I'm just asking you guys to just verify that this expression. You can verify assuming VDD2 as twice VDD, then VDD becomes half its final value, and you can see that this value will reduce to RC ln 2, and it makes sense, right? So one interesting thing to notice here is that by using a diode, I was able to build an RC circuit which was able to reach its final value in a finite time, right? Even theoretically, it has reached its final value in a finite time. So if you took a conventional first order circuit, the time it takes to reach its final value is infinity, ideally. But here I was able to reach its exact value in a finite time. Such things are possible if you use diodes. Diodes are nonlinear circuits. We can build some very interesting applications using diodes at later part of the lectures. We'll talk about the diode circuits, and you can see the crazy things that you can do with diodes. Okay, and that's one big advantage of diodes. You will see such behavior. So if you see, right, at this point suddenly the curve was so far increasing like a linear first order charging, suddenly it becomes flat. So such abrupt changes are possible if you use diodes. Okay, so that's it. So this is one circuit. I wanted to talk about this because if you read any data sheets, you may find a circuit that looks like this. So you have to keep in mind this resistor will determine the gain of this comparator. You might end up decreasing the gain if you decrease the resistor, which we don't want to do. So if you don't want to decrease the gain, just operate this guy at a higher supply voltage. Okay, so that's one thing to keep in mind. Higher supply voltage, and use a diode so that the output node doesn't exceed VDD volts. The other interesting aspect of this open collector, open drain outputs, which is one of the big reasons why they find applications, is that you can use this open collector and open drain output based comparators and perform some very interesting logical operations by just shorting the outputs. Okay, you can realize some very simple logical OR and logical AND operations by just shorting their outputs. Now let's say I took the outputs of two such comparators and shorted their outputs and connected a single resistor to the supply voltage VDD. Now I'll assume the differential voltage to these two comparators are VD1 and VD2. So keep in mind, this is the mathematical representation of a comparator with an open drain output, open collector output or open drain output. This is something we discussed in the beginning of the lecture itself. It will be very useful now when I'm analyzing the circuit. So what happens when VD is greater? I'll just look at this circuit. When VD is less than 0. If VD is less than 0, the output has to go to logic 0, which means this transistor will be turned on. The output will be pulled to logic 0, right? If VD is less than 0, this node will be at a huge negative value, which means this node will go to a huge positive value and output will be pulled to logic 0. So if any one of the comparators output goes to logic 0, then the output will go to logic 0. Whether this is trying to pull it down or this is trying to pull it down, the output node is shared now. So if any one guy tries to pull it down, the output will go to logic 0. Okay, so the output will go to logic 1 only if both these transistors, both these comparators output is not trying to discharge this output node. Okay, so which means VD1 should be greater than 0, then this the triangle transistor in this comparator will be cut off, and this comparator's output is also trying to charge this node to VDD, which means the transistor, the final discharging stage in this transistor is also cut off, in this comparator is also cut off. So then you have a proper path for charging the output node. So what operation do we perform? If both VD1 and VD2 is greater than 0, so that is I can use these comparators to compare two different voltages. So that's like checking two different conditions. If both the conditions are true, see, a comparator is like you can look at it like a condition checker, right? It's checking some condition. If some voltage exceeds a certain level or some voltage level, then the comparator flags a logic 1 or logic 0. Okay, it flags a digital output value and which tells you whether the voltage, the comparator's inputs are greater than or less than 0. So if both the conditions are satisfied, if both VD1 is greater than 0 and VD2 is greater than 0, then only then the output will go logic high. So if both are true, then your output is true. So that's an AND gate. Okay, so if I short circuit the output of two open collector open drain output based comparators, I realize a logical AND operation. Okay, so if you guys recall, we were using logical AND gates in window comparators, and you will normally see if I'm building window comparators using open collector or open drain output based comparators, you won't have to use an external AND gate. You can simply short circuit the two outputs and you naturally get this AND gate for free. Okay, that's another advantage of open collector and open drain output based comparators. So I can extend this to multiple comparators as well. Let's say I have 3 comparators which are all checking 3 different conditions. When will this output be charged to logic high? When all the 3 conditions are satisfied, when all the 3 conditions are true. VD1 is greater than 0, VD2 is greater than 0, VD3 is greater than 0. Okay, so I'll call VD1 greater than 0 as true. Okay, anytime this input is, the differential input is greater than 0, corresponds to, let's say, a condition true. If the input is true, then the output will be also true. Okay, if all the 3 are greater than 0, okay, then only then this output will be charged to VDD. Even if a single discharging path is on, this output node will be discharged to 0. So for this output to be charged to 0, all the 3 comparators should have no discharging path, which means all the 3 comparator input should have this condition. The differential input should be greater than 0. Okay, so that realizes a 3 input AND gate. So that's one big advantage of the open collector or open drain output based comparators. Okay, so the next one is what we call as the push-pull output based comparators. What is a push-pull output based comparator? A push-pull output based comparator is one where it can push and pull current into the output node. Okay, it can either push current or pull current out of this output node. So it's called the push-pull output stage, where you don't need an external resistor for charging or even discharging. Okay, the comparator itself will take care of it. So if you pick the comparator with the push-pull output stage, then it doesn't need any external resistor to be connected. Okay, and the final output stage will resemble something like this. It will look like a CMOS inverter. Okay, it's a CMOS inverter is nothing but a common source amplifier. That's also a very high gain amplifier, where the discharging path happens through NMOS and the charging path happens through PMOS. Okay, so here both the charging and discharging path happens through a transistor. And generally this push-pull output based comparators are faster than the open collector or open drain output based comparators, because you are putting an external resistor, and then the logics for when the outputs are getting discharged, the comparator has to fight with the resistor to discharge the output node. So you don't have all those problems here, and therefore it is faster compared to an open collector or open drain output based open collector or open drain output based comparators. Okay, so push pull output comparators, if you pick that, they will be slightly faster compared to an open collector or open drain outputs, and they don't need any external resistors. Okay, so that's one advantage of push pull output based comparators, and they can be used in slightly applications where they are required for faster, they are required for high bandwidth circuits. Applications where the bandwidth required from these comparators has to be higher. Bandwidth means speed. They have to operate at higher speeds. Now, since we are talking about speeds, anytime you take a digital logic gate, if you guys analyzed any simple CMOS inverter based circuit, when the output of a CMOS inverter goes from, let's say, logic 0 to logic 1, if you see, the CMOS inverter's gain is usually maximum at this point when it is at the high gain point. Okay, so let's say I've applied initially the output is logic 0, I've applied logic high, I've applied a huge voltage, and or even input can also be changing, but let's assume I've applied a logic high. When I've applied a logic high, the output will now I've applied a logic 0 to this, so the output will now start charging to VDD. Okay, so when it is charging, the transistors, if you look at this NMOS, NMOS transistors or PMOS transistors, they go through different regions of operation. Usually when it is in this region, when it is closer to the mid rail, your transistors will be in saturation region. If you guys recall, for a fixed VGS, I'm reiterating this point because we analyzed this previously for TTL logic as well. For a fixed VGS, a MOSFET will carry maximum current when its VDS is higher. Okay, or it will carry the maximum current in the saturation region. It will carry lower currents in the linear region. Okay, because VGS is fixed. For a fixed VGS, as I decrease my VDS, it will carry lower currents. Now in this path, whenever you are in these two regions, when you are close to the supply rails, whether logic high level or logic low level, whether it's the charging path, charging happens through PMOS or discharging happens through NMOS. Charging path or the discharging path, your transistors in this region, your PMOS will be in linear region. When it is close to the supply voltage and PMOS is still charging it, the PMOS will enter linear region. And when the discharging path, NMOS will enter linear region at this point. Okay, so the devices will be in linear region. In linear region, the devices will have lower current to either charge or discharge the nodes. So that's where your rise and fall time, most of your rise and fall time comes in this region, because this is where the devices are really slow. They are really fast in this region. So what if we operate our devices in this region itself? Okay, so that means I would want my transistors to go to either cutoff or in saturation region. I don't want them to be in the linear region of operation. Then I should not let my voltage levels go above a certain level and below a certain level. I should let my logic high and logic low voltage levels remain within a small voltage range. Such a voltage signaling is what we call low voltage differential signaling, or LVDS. In an LVDS signaling, your output voltage is normally restricted between two voltage levels which are farther away from the supply rails. Okay, so I can improve the speed because my transistors will be in saturation region or cutoff, and that's how I get good speeds out of it. Because my charging path will be faster, discharging path will also be faster. So a low voltage differential signaling uses differential amplifiers for this, and if you see a low LVDS output based comparators will normally be a differential input, differential output comparators. Inputs will be differential and outputs will also be differential. So at the output stage is going to look something like this. So if you guys take a differential LVDS comparator, LVDS output based comparator, the last stage will look something like this. Okay, so this is the positive and negative outputs, or this can be VO minus and this is VO plus. Okay, so normally they operate with a fixed current source. So you guys can think about it like if you guys have heard of this word called current mode logic, or you can think of a circuit, since you guys have done some basic course on differential amplifiers. I can take a circuit like this. Okay, so if I apply a differential input to this differential pair, the output voltage, the output node voltage here, see, if you apply any differential voltage greater than root 2 times VO drive, and how do you get this root 2 times VO drive condition? I have derived this result in one of my old lectures on microelectronic circuits, You may have to go through differential pairs if you are interested in learning about this, because it's a slight a bit of a derivation. I don't want to go there right now. I'm just telling you that if you apply a slightly large differential input voltage, the current will fully switch to one side. This transistor will be cut off. If you apply a slightly large negative differential voltage, this current will be fully switched to this side. So if you plot the differential voltage, it will go to plus IR minus IR, plus IR minus IR. It will look like this, IR minus IR. Okay, so such a signaling is what we call a low voltage differential signaling. The output stage of a low voltage differential signaling will look like this. Okay, it will be a current source. I have drawn, see, usually what happens is the output stage will not contain a resistor. The output stage will just contain two CMOS inverters, differentially driven CMOS inverters with a current. Current is controlled here. Normally, these LVDS comparators, when you are connecting an LVDS comparator, let's say your LVDS comparator's output is driving some circuit, and then let me show that. As far that this circuit is very far away, what we normally do is we connect a resistor we place this resistor very close to the receiving circuit. Okay, wherever this comparator is driving, we place this resistor very close to the receiving circuit. Since we have discussed so many circuits so far, can you guys tell me if I want to convert this? It's a small differential input voltage, right? IR is a differential signal, but it's not equal to the supply voltage. It's much lower than this. If I want to convert it to a rail-to-rail output, what can I do? I mean, of course, you can think of some inverter-based circuits, some digital logic-based circuits, but forget about all of that. Using something that we have already discussed, can you think of a differential to rail-to-rail output converter? An instrumentation amplifier. I can connect an instrumentation amplifier, right? An instrumentation amplifier will amplify differential voltage, input voltages, and provide a single unit output. Even if I provide, let's say, a factor of 3 to 4 gain. See, normally what happens is your differential voltage signals will be in the order of few hundreds of millivolts. Multiplied by a factor of 4 or 5, you can, depends on your supply voltage. You can then appropriately choose the gain of the instrumentation amplifier, so that this is the output voltage reaches the rail-to-rail voltage levels. Okay, so I'll come back to this discussion. So even if I want to use an instrumentation amplifier to convert it to a rail-to-rail output voltage level, I have to place this resistor at the input of the instrumentation amplifier. Okay, the comparator will only be this much, and the value of the resistor will be usually mentioned in the data sheet. If you want to have a certain differential voltage signal level, that will give you the value of the resistor as well. Okay, so yeah, so an LVDS signaling is nothing but it's a low voltage differential signaling. You don't let your output go to rail voltage levels. And the final stage, if you look at the comparator architecture, it will be a differential comparator architecture, fully differential comparator architecture. The final stage will look something like this. How does it work? Think about it this way. Let's say I connect a resistor R here. If you apply let's assume a positive differential voltage, delta V is higher here, and this node voltage goes lower. If this node voltage is higher, your PMOS will be cut off. Okay, if you apply a positive gate voltage, higher gate voltage, PMOS will be cut off, NMOS will turn on. And at this node, I'm applying a negative voltage. Negative means a smaller voltage level here. When I'm calling it negative here, usually it means there is a common mode voltage, and this delta V is lower than delta V volts lower than the common mode value. So this guy turns on, and the current will flow like this. Through this resistor, it will flow through this NMOS. This will be the path for the current. Okay, so it will flow like this. If I show it here, the current's path will be like this. Okay, this resistor I've shown it here itself, I've connected it to the output of the comparator itself, but this resistor will in practice will be placed at the receiving end, wherever this comparator is feeding. Just at the input of the circuit where this comparator is driving, we place the resistor there. Okay, so this current will now flow through the resistor into this output node. So you can see that the differential output node voltage, I've just shown the circuit here. I've removed the transistors which are cut off. This will be your path for the current. Okay, depending on how you measure your differential output voltage, this if I assume this as my positive and this as my negative voltage, your differential output voltage will be minus IR, and vice versa. If you apply a negative delta V and a positive delta V here, the path for current is going to look something like this. The current will flow through this. This will be your path for current, and the differential output voltage will be plus IR. Okay, so that's how an LVDS circuit will operate. It's mainly used in applications where you need high speed. High speed is the very big concern. Then you have to go for LVDS based output based comparators. So this is a chart I took from I think TI's comparator products, and if you look at this chart, on the x-axis it shows the delay. Okay, this is the propagation delay of the comparator's output, the rise or fall time propagation delays. It's an indication of speed. Okay, and you can see the open collector, open drain output, which is shown in this orange color here, they take up the largest propagation delay, therefore they're used for low speed applications. Okay, not in high speed but in low speed applications. And if you see push pull and or open drain, so this is push pull or open drain, they are all in moderate speeds. And here this is push pull is generally, if you see, because this is an option where they give you both the options. This is circuits where they give you both these options, but let's look at only push pull output stages. If you look at push pull output stages, they have propagation delays intermediate to the open collector outputs and the LVDS outputs. Okay, it's intermediate between the two, and then you can go for the push pull output based comparators. LVDS, see, if you guys look at this LVDS output based comparator, it's like a differential pair, and it's always going to draw a constant current from the supply. Therefore they are going to draw some quiescent current. Okay, there will be a finite power dissipation, right? So you can have zero static power dissipation. If your differential input signal is large enough, you can have zero static power dissipation in the open collector and open drain outputs based comparators, at least close to zero. In open color, in push pull output, you will have zero output. You can have zero static power dissipation, but here you will have a finite power. Again, that the trade-off is you get speed. Okay, and the fastest output here is LVDS, which has the lowest propagation delays in the order of less than nanoseconds. So naturally they'll find application in gigahertz circuits. If you want to use these comparators in gigahertz applications, you will find LVDS based comparators. Applications in the orders of tens of megahertz to few hundred megahertz, push pull outputs serve the purpose. Much lower frequencies, open drain, open collector outputs. Okay, so hope this lecture answers all these questions on basics of comparator outputs, on LVDS output versus open collector, open drain outputs, LVDS outputs, and push pull outputs. Okay, so in the next lecture onwards, I'll start discussing more about comparators like Schmidt triggers and so on. Okay, thank you.